We are looking at a Thermo Calculus problem. This is problem 1 from Exam 2, Thermodynamics 1, Spring 2018. And what we're asked to do is calculate or show that dH dP at constant T is equal to 0 for an ideal gas. One of the challenges of this kind of problem is learning how to navigate all the various calculus manipulations to get at the answer you want. I'm going to try to explain how I think about it, but honestly, there's often trial and error involved. I don't always get where I want to go. Since we're looking at enthalpy, usually enthalpy, it appears in a fundamental property relation on the left side, and it generally does not appear on the right side. So I'm going to start with the fundamental property relation dH equals T ds plus VdP. And I can generate this derivative by dividing through by dP and holding T constant. So dH dP at constant T would equal T ds dP at constant T. And then dividing through dP, VdP by dP just gives you V. So now we have to do something about this term. Well, if you look through the Maxwell relations, which would also be on your equation sheet, you will find that there's a Maxwell relation that relates this term, ds dP at constant T, to minus dV dt at constant P. And this is something we can calculate because we know the ideal gas law. It relates PV and T. So this would equal d by dt of RT over P, which we would calculate holding P constant. And this would equal R over P because T is the only variable. And sorry, I forgot the negative sign here. And so this will equal, if you plug the R over P in here, right, then this is going to equal minus RT over P plus V. But RT over P, according to the ideal gas law, is just V. So this is V minus V, which is 0. So that actually solves the problem. The second part is asking us, a solid is characterized by volume of expansivity, beta, and isothermal compressibility, kappa, and we need to derive a formula that can be used to calculate an entropy change of this material from initial temperature and volume T1, V1 to final values T and V. So in this case, we're explicitly told that our variables are T and V. So we are interested, just translating the question to mathematics, we're interested in deriving a function S of T and V. So in this case, I would start with a total derivative. So ds equals ds dt at constant V times dt plus ds dv at constant T dV. So now we need to derive formulas for these two terms in order to get something that we could actually calculate, a formula that we could use. So let's see what we can do with this. I usually remember that temperature derivatives of entropy always end up being heat capacities over temperature. But if you don't remember that, we'll derive it just in a minute. But I know this is CV over T. It's a pattern that I've seen through doing many problems like this. And the way you relate it is, since you have constant V, you want to get something in terms of CV, and so I would use du, because CV is defined as du dt at constant V. So I'll use a fundamental property relation in terms of u, that's T ds minus P dV, and I'll generate du dt at constant V, which is the definition of CV, and this would equal T ds dt at constant V, and since V is constant, dV would be 0. And so what this tells us is that ds dt at constant V, which is what we're after, is just CV over T, which we can feed back into there. Okay, so this term, if you look for, well, I would suggest looking for a Maxwell relation, and you will find one that says that this term is equal to dP dt at constant V. And we need to figure out, notice that we have a PVT relationship, so we might be looking for something related to kappa and beta because of the way the question is asked, because these kappa and beta are also related to derivatives between PV and T. So what I did was I looked at the cyclic chain rule. So this, if we're relating PV and T, so I would say dP dt at constant V times dt dV at constant P times V dP at constant T. Remember that we look for something that looks like it ought to cancel. So T's, P's, and V's. But remember, we're holding different things constant for each variable, so they don't actually cancel. What they're equal to is -1. I guess you could argue that they cancel. So notice now that dt dV at constant P, this is actually 1 over beta V. Compare it to this equation, right? So this is, if you take 1 over this derivative, you get dt dV, right? So that's equivalent to 1 over beta V. And this is going to equal minus kappa V, and that comes from this equation. Okay, we're getting somewhere. And so if you then solve, what you'll find is that dP dt at constant V is going to equal beta over kappa. Notice that the V's cancel in these two terms. So this is actually minus kappa over beta, but you have a -1 here, so when you move it to the other side, it's going to become beta over kappa. And this you can now relate here. This is equal to beta over kappa. And so we now have something that we can integrate. That means that ds is going to equal CV over T dt plus beta over kappa dV. And so if I want to know a delta S for a change in temperature and volume, delta S would be the integral t1 to t2 of cv over t dt plus beta over kappa integral v1 to v2 dv. And you can solve those integrals. This is going to equal, delta S is going to equal cv ln of t2 over t1 plus beta over kappa v2 minus v1. And I think we're done.